Okay, so turning the quiz for chapter 12. We'll start on chapter 13. Okay, so chapter 13 about the spectroscopies. We mainly going to study the proton and MR. The proton and MR depend on the nuclear spin of the H1 atoms. I put the new lecture notes on the blackboard. I think most of you took this organic one before. It's sort of like study those spectroscopy a little bit. So we are going to do a little faster to study this spectroscopy very quick. When you have those atoms, molecules has the H atom in it, each atom have the nuclear spin. Usually, without the external magnetic field, a diameter of proton or the H1 nuclear spinning randomly. So they can either like up and down spinning. If you apply a strong magnetic field, and then they will line up. About half of them line in the same direction with the external magnetic field, we call that B0. And about a little more than half line like little more than half line like parallel as the magnetic field, and a little less than half line like anti-parallel as the magnetic field. So there is a little difference in energy between those protons that line up with B0 or those anti-parallel. And I switched the diagram, the picture as opposite with the textbook. So this gap is the energy difference between those protons that line up with external fields and anti-line up. So the gap increases as this this B0 increases. So B0 here on this side, the external magnetic field is 0. If you increase that B0 larger and larger, then the difference between the two levels is larger and larger. Then those details, how you get those spectroscopies from the sample, and you can read that. You pretty much just put your sample into the machine, and your sample is spinning in the magnetic field B0, and so therefore they will have these two levels separated, and then you apply another additional electromagnetic radiation, not the initial magnetic field. The magnetic field, the purpose of the magnetic field is just separate those spinning into the parallel and anti-parallel. So once you have the difference between these two levels, you apply another signal. The signal, this range, the gap is in the radio frequency. It's not really strong electromagnetic field, a little weaker radio frequency matching the gap. When you match the gap, you can absorb. How can we prove investment those different H atoms in the molecule? Well, H atom bonding to those other atoms, and the electrons in the chemical bond is also produce those magnetic field, magnets, because of the influence of that B0. B0 is that very, very strong external magnetic field, we call that B0. So those electrons in the chemical bond, they also produce the magnet. The magnet produced from the chemical bond were anti-direction as a B0. So those kind of magnets from the chemical bond, they kind of shielding or take away some of those B0 away, make the B0 getting a little weaker. Because those kind of effect shielding, blocking the B0. So the B0 is the external field, external magnetic field is like the one that makes the nuclear has the separation. Okay, now the protons have bonding to different atoms, and those atoms that bury that proton on H1 have different electronegativities. If the atom that carry the H can donate more electrons to the chemical bond, they have more shielding. So that depends on the electronegativity. The carbon is more electronegative than silicon. So people use silicon in the middle bonding to 4 metals, and that will be the one that is most shielded. So then, most of the time, you can try to get some others like even more less electronegative than silicon, then you get more shielded. But usually silicon with 4 metals, that's the standard that's easy to dissolve in the same solvent as those organic molecules. Right, so we will use that as a reference, and so that we call that it's zero chemical shift, and all others compared to that. If you are less shielded or deshielded, and you will have a chemical shift getting larger, and you will see on this side you have a larger chemical shift, and there is zero chemical shift. Zero chemical shift, that means your shielding is same as the reference. For us to get some idea about the structure of the molecules is to recognize what is the influence, what is the chemical shift for those protons in the structures. The effect of the molecular structure on the H1 chemical shift. You remember that the chemical shift is actually the difference between your shielding or deshielding of your molecular proton and the reference. The reference is like the silicon in the middle, and you have a CH3, CH3, and CH3, and CH3. So this guy we call the chemical shift is zero. So if your H atom in your molecule gets by some other atoms take the electron away, the more electron take away from the H atom in the molecule, and then you will have a larger chemical shift. see there are a few examples here. This methyl fluoride, and you have C3 fluorine. So you have a fluorine atom. Fluorine is very electronegative. Attached on the carbon carries other 3 H atoms, but because fluorine absorbs the electron away from the carbon and make the H has less electron to cover it, so the H is deshielded. Deshielded, we call it a down field. So this side down field, the other side up field. The electronegativity influence on the atoms is kind of getting weaker and weaker as the proton getting far and far away from the site. You can see in this example, we have nitro group on this molecule. We know from last chapter nitro is very electron withdraw. So this carbon atom is right nearby this angle 2. If your chemical shape is the most downfield, because this is the most deshielded. So the electron in this on this carbon's H is the most deficiency. You take a lot of electron away from that. Because of that, you have a larger chemical shape. The chemical shape, we use the symbol lowercase delta. The larger the delta, that means the more deshielded, the more electron gets lost. As the carbon gets far and far away from the site of the electronegative atom, and the effect is getting weaker and weaker.
So more further it is, it's going to be more off-field?
Yep, more. Yeah. Then we'll compare later on in more details. So we'll compare initially this C3 by itself is more upfield compared with this C2, because C3 has 3H and H is less electronegative than carbon, and so that's another influence, but it's still considered this, in this example, it's still considered far away from the angle 2. Now here we'll compare those methyl, methylene, and methylite. Methyl, methylene, and methine. Methyl means C3, methyl group is C3, and methylene is C2, methine is CH. That means you have that H, see how many other H nearby. Just compare H with carbon, for example. H is less electronegative than carbon, so you have more carbon, you get more electron wave loss. If you get more electron wave loss, that means you have larger delta downfield. You can see from this few examples, you can see this guy is for the methine H. When there is 3 carbon on this carbon, there's only 1 H. The delta is 1.6, and this is the methylene at 1.2, and the methyl is 0.8. The methyl compared with methylene and methine, and methyl is the one that's the most shielded. Most shielded is to go upfield. And the effect of the electronegativity is also cumulative. So if you have like a C3 and a Cl, and you only have 1 Cl electronegative, and your delta is very small, 3.1, and you put more and more Cl, those electronegative atoms, your delta getting larger and larger because it's getting more and more deshielded. So now let's see this problem 13.4. Identify the most shielded and least shielded atoms. The first one is this molecule. So as indicated, we have this Br and we have this 2-bromobutane, and the most shielded is this metal, because metal is more shielded than this methylene. And in another sense, this metal is far away from this Br. So metal and metal here, And this method will be different, like more downfield than that one, and like those D-shielded than that one, because this one is closer to this carbon has to be direct. And the most D-shielded or the least shielded over with this one, because this edge is right on this carbon that has the bromine. So if I tell you those few numbers, the observer temperature shift 4.1, and 4.1, the delta 4.1, so this guy should have so this guy, I just number, should have the most D-shielded temperature shift, which means downfield. Downfield, that means you have a larger delta. If you have those numbers, you want to sign it. The 4.1 should be that age.
So does for shielding, would like inductive reasonings be like more of a reason why one's more shielded than the other, or would steric hindrance be more of a reason why like that CH3 is more shielded than just the H1?
Well, the steering hindrance little influence, because later on we'll see those, if you have those like those double bond, and that's not that important. More important is the electronically. Okay, the second example is this. You can see the numbers and then make sense. So this H is the most D-shielded. Most D-shielded have a larger delta 5.9, because this guy has 2 CL in addition, there is not CL nearby. And next one probably this one. And then the most shielded one in the metal, most shielded you will have a small delta. The last molecule is this tetrahydrogen furan, and this oxide is very electronegative. Pull electron away from this. D-shielded will be downfield. Downfield, that means you have a lot of delta. So on the exam, like on the quiz, I will give you those tables, and you will have time. Just try to look at these tables, see the patterns.
Sorry, you said down field, some more shielded?
Downfield and D-shielded. That's
Downfield is less shielded.
Yeah.
Okay.
Now here we just
more shielded.
upfield more shielded. So here we just see those electrons withdrawing group. Sometimes because the electron is structure of the molecular structure, you're creating a local magnetic field. And not only because of the electronegativity, the local field from the, for example, from the bending ring, and that can strongly like anti with your incoming B0. B0 is the one that is responsible for the separation of those spins. And then your proton in that field that is anti with the B0, that will be most D-shielded, even though you don't have those electronegative atoms in it. Yeah, right here. So when you have this double bond or the bending ring, you create this kind of local magnetic field. Those magnetic field in those small blue line is representing from the molecule. And this large arrow is so-called B0 is applied external magnetic field. And this B0 is one that is responsible for the separation of those spin like anti-parallel and parallel. And you can see if something like something in those areas like those where those H was, and you can see this this area the H is located, and those arrows of those small blue arrows is offset as the error of this B0. That means it's kind of take away some part of your B0. So those kind of effect, we call them D shell. And D shell, that means your proton will have larger delta. Okay, so similarly here you have this bending ring, and you can see those small area, the blue arrow here, and the small blue area here is in the same direction as the larger green arrow. So that means your normal field actually enhance the B0. So make your B0 getting like larger. So we call that D shell to enhance the B0. So therefore your separation getting larger. Now you compare those this few effects, and even those nearby, they are not really on the ring, on the bending ring, or on the double bond, and you still have the similar effect. Right. So we have, for example, we have two metals here, one metal nearby the double bond. If you have H here, and you will know that H is de-shielded, and will have a larger delta compared to the usual H on the bonding to the metal or methylene. And here you have compare this metal with that metal. That metal don't have that normal field like what we saw in the picture from the double bond, so therefore it's like more shielded and more upfield. Right. Now the other one is the triple bond H. The triple bond H is kind of lying between the double bond H and the single bond H. So the triple bond H in the area, so those are really like you can see that is those small area like shielding away the B0 anti with the B0, because the H in the triple bond will be somewhere here, and here you have this external field going up, and the magnetic field from the local, from the triple bond, just having opposite with the B0. So it's kind of shielding. So in that effect, your chemical shift should be outfield, get bigger, like a small number. But you consider this as this hybridization of the carbon in this triple bond is sp, and then we know sp hybridization is more electronegative. More electronegative, that means it will put the electron away, more electron away from the H is de-shielded, so therefore these two kind of opposite. Okay, now let's see, we'll try to assign the chemical shift. I'll give you a molecular structure, and I'll give you those different number of delta. So you have 1 in 4.8 for this example molecule here, and you try to assign those numbers. And so we know the H bonding to the double bond carbon is more de-shielded. So this H here. And you should have the number like 4.8, the largest delta. And you have here 2H. Or let me just go back to the. And you have that 2H 4.8. That's the most de-shielded because they are like closer to the on the double bond H, and in that area, you know that. So if you have this here H, and your external field goes this way, and your local field also goes this way. So these two magnetic field will enhance each other. That means you really like de-shielding. So you don't have the shielding to block in the B0 anymore. Not that much. So if you don't block the B0 will make your energy level getting more and larger gap. Larger gap compared with the reference. So there's a difference between this part here, this part here. So this part here is 2.2, that part here is 1.6. Even though both of them are the mass thing. The reason for this have a lot of delta is because this is closer to this double bond, and you will have a similar effect like this. So you still have a local magnetic field and it goes up and in the similar direction as like the external one. Right, now if I give you this molecule, have the binding ring, have all those H in it. So we know that H on the binding ring is the most de-shielded. Most de-shielded will have the largest delta. So there's a delta like 7.2, and I will give you those kind of data on table. So just try to assign those numbers, and obviously this 7.2 will go to those H on the binding ring. And then you have two group of H. There's one here, there's one here. And so 7.2 work for those H, and 5.1 work for this H. Even though this H is, I think you will see those H, so-called benzylic H. Benzylic H referring to this two H here. According to the table, if you simply have those benzylic H, for example, toluene H, those H from the background of the binding ring, toluene, and you will see the number is somewhere between 2.3 2.8. But here, this 5.1 doesn't match any of those numbers. That is because you have those cumulative effect. So you have this binding ring will make this more like de-shielded, and this oxygen also makes that more de-shielded. So these two effects enhance each other. So you have the number 5.1 doesn't match the number, but it's understandable. It's because of the de-shielding those local field from the binding ring, and also from the electronegativity of that oxygen. Now the other one kind of, the last one kind of matching pretty good, but that means you have this CH adjacent to a carbonyl, referring to those CH adjacent to this carbonyl. The number should be somewhere at 2.0, 2.5, and then you can see the 2.0 here. That means this 2.0 will be for those CH3. Okay, so that's the result when you sign those numbers. Okay, so next example is you have this molecule, and you will see the result for the delta is as follows. This one is what we saw before is simply because of this result is simply because of the electronegativity of this oxygen. And this metal, usually the metal will have the more shielded, have small number than those those kind of methylene. But here, this number, this CH3 here have a lot of numbers than this methylene, this CH2. If you don't have number should be smaller than this number. But now you have this oxygen, and this oxygen is more electronegative. So pull the electron away from the atom, and because this has a larger number, which means d shell is downfield compared with that one. Yeah, you can see this metal here. So this metal at the end is far away from the carbonyl and get a small number, but this is shielded. Yeah.
Why is the proton the 2.3? Why is that one bigger? It's a bigger number or less shielded?
Yeah, that's shielded more like de-shielded. 2.3. Yeah, 2.3. So you can see these two guys. So we have a carbonyl here, and this one 2.3, and this one is 1.7. And both of these carbon here, we call them methylene. Right? We call them methylene. Which means they are CH2 type. CH2 type. C2 type, this 2.3, and that one is 1.7, is because this methylene here is closer to this carbonyl.
Without the two, the other.
2.0.
Yeah, why?
2.0. So usually this guy is C3. Right? So C3 is usually more shielded than those.
The 2.3 is C2 one, C2 is one.
Yeah. This also C2. This also C2. C2 here, and C2 here, and this is C3.
Oh, I mean, so why? I'm just comparing the 2 and the 2.3.
Okay. So okay, so this 2.0 is less than 2.3. That's because usually you will see the C3 have a smaller number than C2. So C2, that means you have 2 H replaced by carbon, and carbon is more electronegative. Oh, that don't have H. So that's okay, right? So that don't have H. Yeah, that don't have H. Yeah, this 2.0, usually you will see that number for the 2.0 is somewhere like 0.9, 0.8. It increased from 0.9 to 2.0 is because of the carbonyl. The carbonyl has oxygen on it, pull the electron away. Make this metal de-shielded. Okay, now let's clarify that again. Okay? Usually, if I give a structure like this, if I give you this, no carbonyl, okay, and this is C3 here, and this is C2, okay, and this number will be somewhere like 0.9, and this will be 1.2. Without the, maybe better put it here. This is CO2, without this also CO2, and both of them will be somewhere like 1.2. Okay? Now, if you replace this guy by the carbonyl, and you should still have a small number of this part, and compare with this one, but it's starting with a small number. The metal is more shielded than the methylene. Without the carbonyl, you have a small number, 0.9, 1.2. You add the carbonyl, you still have a small number. But both of them getting larger. Does that make sense?
So why is that more shielded? Why is the left one shielded from the right?
Because this CD3 has only one carbon on this carbon. Carbon is more electronegative.
Oh, so the other one has the O and the C, so which are opposite.
Yeah, so this carbon has a C and the C has two carbons on it.
Okay, that's, yeah.
Right, you can see this result here, okay? And you have this one, the blue one is C2 methylene, and then the red one is C3. Okay. So remember we said the C3 is more shielded, is to have a small number, and you can see here you have a small number. But this small number not really matching the number we saw there, like usually if you don't have any other atom on it, just 1 9. And here you can see the number is about 3.5, 3.4. The reason is this is not the simple metal here, you have metal 1 to 0. Right, so the chemical shift is one you want to use to get some information about your structure. The other is how many signals you have, like in the last spectrum. How many signals you have will tell you how many equivalent type of age you have. And this spectrum, this proton and electron tell you that molecule only have 2 signals. That means you only have 2 type of equivalent proton. And that makes sense that C3 and C2. So all the red 3H are the same. So they will produce the same chemical shape. And both of the 2 blue H are the same. So both of them produce the blue shape. To identify how many equivalent protons in the molecule is very, very important. So how do you know which H are different, which H are the same? How many of those different ones, different sets? You can just use the so-called replacement technique. If I give you a molecule like the protein, you can replace H by, for example, PR or Cl. Then you see what is the molecule's name. Okay? And if you replace, like you get a different name, that means those protons are different type. At the beginning, you use the technique, and then after a few examples, you will recognize what are equivalent and what are not equivalent. So for this protein, obviously you can see you have 2 sets. Okay? So this is C is 3, and C is 2, and C is 3. So this C is 3 on the left side, that C is 3 on the right side are the same. Because you replace the C is 3 here, you get a 1 chloropropane, and you replace the C is 1 is there by chlorine, you also get a 1 chloropropane. But if you replace the middle one, you get 2 chloropropane. So we have 2 sets. Both of these give you 1 signal, then the middle one give you another signal. Then you will see you have 6 protons give you 1 same signal. You have 2 H in the middle give you 1 signal. Then do you have information from the spectrum? Definitely yes. You will see those so-called integration number and tell you one like those signal have how many protons in it. So depend on the chemical shape, depend on like how many signals, depend on how many protons in the signals, and then later on we'll see another pattern called those split. So here in that example we'll see your spectrum is very simple. Each signal is just a very straight outline. Sometimes you will see so-called doublet, triplet, quartet, and so on. So whether you have a single, double, triple, that will tell you how many nearby equivalent H you have. Right, now let's see this problem 13.9, and we have a few molecular with name, and you try to identify how many signals for each molecule you can get. Okay? So this problem A is actually the one bromo like butane. We don't have the chlorine on A. The chlorine on A is just you just use it to identify whether they are the same H or not. Okay? So this problem actually is like this. So these are our initial molecular, and you want to identify how many different signals you can get. So here you will have a 2H, and that will give you one signal. Well, that one signal will have a triplet. Well, you will split that signal, so the integration will tell you have 2H, and then you will see something like this. You have a triplet like that. How to do that triplet? If you have a triplet, that means your three chemical bond weight, you should have two same H. So maybe sometimes maybe two chemical bond weight, okay? But usually three chemical bond weight, those kind of H can split in the signal. Okay? So if you call these two H's are your A, HA, then this is HB and HB. So two HA are the same, two HB are the same. And here will be our HC and HC. And here you should have a 3H, HD, HD, and HD. Right. So therefore, we will have a full set of signals from this. And then you should be able to also like predicting what are their chemical shape. Okay? So the chemical shape is HA. Okay? So that delta HA will be larger than the HB and will be larger than the HC. This is very simple, larger than the HD. Because as A is closer to the BR, and when the carbon getting far away from the BR, you get more and more share of this because you don't take too much electron away, and you will get a smaller and smaller delta. So this is so somewhere I think this is the real spectrum for the 1-bromobutane, and you can take a look and see that matching what we said. Similar for this one. This one you will have a 5 set of signals because you have a H on the active. This one? Yeah, so this one you will have a CH3 and CH2 and CH2 and CH2 and O and H. Okay, so now here if you also draw those H out. And for example here, and when you have the H like a 3-bond weight, and they will split in the signal. Usually this is the most common pattern for the splitting. Sometimes when you have a double bond and you have the H on one side, cis H, trans H, they can also split their signal, but those splitting very weak. Now here you can see this, let's see how this is our HA, and this is HB, HB, HC, and HC. Now HB and HA can also like three bond way. Usually this splitting from the HA to HB is negligible because those H in the on this HA usually were in the hardened bonding. And then the HA and HC, HB and HC, so this HB and HC, they can split each other. And you will have two more H here. Okay? So you can consider like how many like signals, one signal from these two HB, and you will see how many lines, because they are triplet or doublet. HB will be the triplet. And HC will have, so this D and D, even though C, B and D are really not that the same, they were different, right? Because this D is far away from this oxygen, and B is closer, right? So like if you have those very well like dissolve resolution high, you will see your line is more complicated, but for simplicity, you can just add in this two together, you get 4, and use the n+1 rule. If you have 4 those at H nearby, then +1, you will get that means you will get 5 lines together as one signal. Okay. So this HC will have 5 line signal piled together, and then this HB will have 3 lines together called the triplet. So those information is very important to figure out what is the structure of the molecules. So H1 NMR will tell you some good information about those H. How many H on what carbon? Right. So now let's see this example. So in this example, you see you have like this. 2 here on that carbon. Okay. Now here, we should have 3H. And here we'll have 2H. And here we'll have 3H. Right? So the one that will have the more like downfield should be this one, this H. And then this is 3H. We have a single H.
Because it's not big ones away from another H.
Yeah.
Use the n+1 rule.
Yeah, use n+1 nearby. Yeah. If you have like a 3 bond away and 2 atoms, your signal will be triplet.
Compared to the other, the 2H.
This 2H here, very good. And then you can see 1, 2, 3, 4 bond away. So this 3H will not split in this 2H. Okay. But here, this 3H is 3 bond away from that quartet. Yeah. Okay. So those signals will be the quartet. Then this 3 here will be the triplet.
Why is that a quartet? Is there 2 hydrogens?
Okay. Quartet, that means the n+1 rule. So that means the nearby H is 3. And that 3 come from not this three. This three is a 4 chemical bond weight. 4 bond weight, that will not,
Oh, so it's obviously good because
yeah,
there's 0 plus
yeah,
1.
well, zero plus one. It's zero nearby. Right. So and this kind of splitting, and we talk about usually the splitting like 3 chemical bond weight, or you can also like say this kind of difference has only 2 chemical bond weight, and those kind of splitting usually is very weak.
Can you go up for a second?
Okay. Yeah, so this is what you talk about the spin splitting and proton NMR. Then N plus 1 rule, right? So now predicting, you have so obviously these 3 are equivalent, H or HC. And these two are equivalent and the same for them, or HB, and here or HA. Right? So your delta, this one will be the one that is the map. Yep. This will be the signal light. This is the port head, very good. And this one is the triple head. Okay, now the N plus 1 rule is because each atom they can be parallel or anti-parallel. So you will have those kind of if there is a HA, so this HA will split this signal from this 3 HB, and this 3 HB was splitting this signal of HA. So that's and why you will have the N plus 1 rule. So you have 3 nearby H1 equivalent nearby, and that 3 H1 nearby can all the 3 parallel with B0 or anti-parallel with B0, and or you can 2 parallel 1 anti-parallel and 2 anti-parallel 1 parallel. So you have those kind of possibilities. So therefore you will have 1, 2, 3, 4 signals. Okay, so more practice. The first one is 1,2 dichloroacid. So you will have C and C and H and Cl, and here is also H and Cl. Right? And for this molecular, if you have 4H and 2H on this carbon, 2H on that carbon, and you have 2 Cl, actually all the edges here are the same, right? And the same edge will not split. So if you have this molecule, you make your AMRs, like the proton AMR, you only have one signal. And no splitting, no double layer, no triple layer, just one single signal. Now the one trichloroethane will be similar. Okay, so this is A. Now for B, you will have on one carbon you will have 3 Cl. So here you have 3 Cl, and here you have H, and H like that. And this is probably even more clear why there is only one signal. One signal, single leg. Right? All the 3 H on the same carbon. So I think the C is the same. So this C is the same. C is 1,1,2 trichloroethane, and you will have this. Okay. Now let's identify how many H are there and what is the splitting pattern. Right? We pretty much have like these 2 H are the same, these H are the same. Yeah, you will have splitting this H or splitting this signal from this 2 H double layer, and then this 2 H will split that H into a triple layer, right? Because you have n plus 1 loop. And from the integration, from the signal, you will see the signal with this double layer, and you will tell you there is a 2H, there is number 2.0 or something. Yeah, so this one will be the double layer, and this one with the triple layer. Right? Yeah, so this one has these 2 nearby. Yeah. There's only one H, and 1 plus 1, 2. So maybe these 2 will double layer. And then you can also use what we learned before. So this one will be, so this H, this triple layer will be more downfield. There's some common splitting patterns. One common splitting pattern, you will see, you can also use a little bit in like the lab. We will have that the C13 NMR lab. So I will give you spectroscopies and you decide the structure. So I pretty much write those problems on the lecture notes, and I put these lecture notes, the full version lecture notes on the blackboard. So you can download it and take a look. So we'll just go briefly, very quickly here. One pattern is sort of the acyl group splitting pattern is the triplet and quartet. So triplet and quartet is because you have when you have like an acyl or something like maybe the acyl bromide, so you have this C and C and this 3H and this 2H, right? And so the BR is like the one that is more electronegative. And then we have this carbon has 2H, the methyl has 3H. So the methylene, the carbon with 2H is methylene, and that 2H obviously is different than that 3H. And then that 3H will split the signal of the 2H into the quartet. The 2H was splitting the methyl's signal from the 3H on the triplet. So you have this sort of the triplet and quartet pattern. So this example is you will see quite a few of the S or group, and then you will see this triple S and quartet pattern. And sometimes you will see like two of these S or groupers. We see two S or groupers if the two S or group are the same, and you pretty much will see one pattern of the triple S and quartet. So the first one, you have a S or grouper on the right side of this ether, right? So this, you will have this quartet and triplet. Right? Now here you have this C2. This C2 actually will be the single net because this, nearby this H2 is like 4 chemical bond away. So 4 bond away, this 2H will not split in the signal of this 2H. This 2H can split in the signal from the red H. So another azure here, and measure here. And this measure will be, you will see a single line because there's 3H here, and those H here will be 4 bond away from those H. You can either see 4 bond away or 3 bond away, or you just see the H like on those H. If we split in the signal, and this will be on the, at least it will be on the adjacent carbon. If you only on the adjacent carbons and there's no difference, then you will not split. Right, so if I have, so if you only have 2 carbons like this, so technically, this H on the right side can split into the signal from the left side, but if you only have this single structure, the SN, and all the 6H, all these 3H, those 3H are the same. So the same H will not split. You can change this into this SN into an S or grouper by replace one of those H by some other grouper. If you replace this H by CL, then you will have the typical S or splitting pattern, triplet and quartet. So the reason I said you don't have to count how many chemical bonds, because those structures, you can visualize the structure, you can count in the chemical bond, right? But otherwise you will see this is adjacent, nearby. Then the H on this one can possibly splitting each other. So then this S are here, this S are here, S on the left side of the O, S on the right side of the same. But this is different like this. So these 2 H, these 3 H are different. So therefore you will see the typical, just one set of quartet and triplet. This set of quartet and triplet is same as this set. Right. Now you have the you don't have to do that. So you have these 2 S on the benzene, and you say you have 2 S on the benzene, so this S will produce the triplet and quartet pattern, and this S will produce that triplet and quartet pattern. These 2 S are the equivalent, right? Then the then why those aromatic H was not split in those 2 atoms? Why this H will not really influence the 2 atoms? You can see this atom still keep that triplet quartet pattern is not really influenced by this H. So this H On this carbon, you don't have any H. Right? And then you can see this, the aromatic H, all the 4 H just synchronized. There's no split. Symmetrical, all the H here, all the 4 like aromatic H are the same. Right. So we usually use like the proton AMR to get those detailed structure, how many H on what kind of carbon. By example, those integrating from the spectra. By example, how many whether you have a triple lead, double lead, and by example like those chemical shape. Sometimes you can get a very quick like the carbon the molecular structure by examining those carbon like NMR. The carbon NMR is much simpler looking than the proton NMR. The principle are similar. So you will not see so many like let's compare this two type of NMR. In the proton AMR on the top, you will see those signal is complicated because of the splitting. And then you see this the carbon AMR is very simple. Each signal just one like a simple line. So therefore, you can quickly find out what is your structure of the carbon. So if you have 5 signal from the carbon AMR, which means you have 5 different carbon. Okay? You will see the reason for the non-splitting very simple spectrum is because you don't see the splitting too much between carbon and carbon. With carbon like carbon-13 isotope is very less abundant. So you have this molecule naturally occurring, and you will have a very small chance of one carbon-13 on one side, and another carbon-13 nearby 3 bond away. So therefore, the splitting is very weak. You can also possibly have the splitting between carbon and the proton. But if you have that splitting, then your spectroscopy will very complicated. So they designed the spectroscopy eliminating the splitting between carbon and H. Then you will lose some information because the information you can get by integrating the signal tell you how many carbon, how many H. But if you get rid of the splitting between the proton and carbon, and so then those near the carbon has more H, will have like the signal a little stronger. Then if you want to do integration, that will not tell you the true number of how many carbons, because those signals strengths also have the information about how many H you have. So this simple one that you can use to very quickly identify how many different carbon in your molecule. So therefore, we will have the lab. I will give you mainly 2 spectroscopies, 2 spectrum. One spectrum is the H1 NMR. The other one is the carbon-13 NMR. You can use this combined together, pretty much will find out the molecular structure. So if I give you a molecular like this molecular blue pair bending like this, similar as you identify whether you have the same H or not, you can identify whether you have the same carbon or not. Okay? And so we remember those different carbon with different letters, and you find out about this structure on the top, and you will have like altogether seven the carbon-13 AMR signals, same line. Okay? The same line come from on the bending. You see some of those letters. So this one, I just randomly number them 1, 2 to tell you how many signals. So this will be one signal. This is a different carbon. Okay? There's another carbon will be different. Okay? And these 3 will be different. Okay? And 4 will be different. Okay? And 5, 6, and 7. And then this will be also the 5, and this will be also the 6. So you have 7 signals on the carbon-13 AMR. Any questions? B they have 6 signals. 1, 2, 3, 4, 5, 6. So that's 6 different carbons. And the C also have 6. So C is 6. Pretty much like all these 3 syntheses this are metals. These metals elements are the same. There were 1, 2, 3, 4, 5, 6. Now, so if we have these 3 metals on bending, then you can see all the 3 metals on the bending are different. So there, the 3 metals on the bending, so the M and M are the same. This one, and this one are the same. Now here we have 3 metals. Each of these 3 metals are different. And then each of these carbon on the bending are different. So this one is very symmetrical. What really all those metals are the same. So therefore, we all call them X. So altogether, you have 3 signals. The 3 signals come from the 3 metals. Now on the bending, you just pretty much just only have 2 different ones. On the bending, you have 6 carbon. So this Y and Y and Y are the same. So all the 3 Y carbon on the bending have a metal on it. And all the 3 carbon on the bending has, we label them as Z, have H on it. The electronegativity on the chemical shape for the carbon-13 AMR is the same as for the proton AMR. So therefore, you will see that if you are more de-shielded, you will have like more down field. Okay, and you can see this set of number tell you the chemical shape for the carbon that is blue. Okay. And the red number is the chemical shape for those H, that is red. Okay. And you have some similar pattern. Right. So this another point I want to see is the chemical shape for the carbon-13 AMR have a range like from 0 to about 200. For the proton AMR is about from 0 to like 12. program we can understand is very similar as we saw before for the proton NMR. So we have a PR on this side, we have a CR on this side, and the CR is more electronegative. So therefore, you can use the CR more de-shielded the carbon or the proton on that carbon, and you have that third high is 43. Right? On the other side, you have PR. PR is less electronegative than CL, so therefore it's even more shielded, so therefore we have a relatively small number of 35. The middle one, not really close to CR or the BL, so therefore it's more shielded than most of the other carbon. You get like 30. So then the hybridization has a very dramatic influence on the carbon's certain chemical shape. Okay? So for those double bond or the benzene ring, you will see the number is about in the hundreds, and compared with those sp3 is about like 50 and 40. So that is the pattern you can examine when you have the table. As you consider this molecule, you want to assign the numbers to these three type of carbons. Okay? So we have even though in details the carbon in the benzene ring were a little different because on this side you have this methoxide, on that side you don't have the methyl. Okay? So if I tell you the number is 20. 55 and 57, and you can quickly assign a number. 157 will be for those carbons on the benzene. And the next number, 55, will be for this Z. But this one is closer to the O. All right, so that is the result. And closer to O, oxygen is more electronegative, and then more de-shielded. Do we have any questions about that?
Is the reason why the C on the 20 is less than the 55 is the oxygen?
Okay, good question. The reason is that X is also the C3, the Z is also C3, right? Now what is like the difference is because in this example is simply because of oxygen is more electronegative. Okay? So if you compare like before what we did, when we compare the proton NMR like that, you have O here, CH3 here, and you have CH3 here. For the H1 NMR, then you are predicting this method, the delta for this H1 NMR, it will be a little different than what we saw here. It will be larger because of the so-called ring magnet. We have the benzene ring magnet. If you have the NMR, this one is like more like de-shielded than this one.
Oxygen is shielding
also de-shielded the C3, but then de-shielded simply because of the electronegativity. Now if you have the bending ring produces the magnet. I think at one point we were confused about that, and it will produce the current of let's see, your magnet from bending ring is looks like this. Goes up, and this area like this. So here it goes down, and then here, so this is your B0.
So, basically because oxygen is more electromagnetic,
Yeah.
it attracts electrons.
Mhm.
And that's why it has a higher delta than carbon on the
Yeah.
index.
The higher number, that means you have either you think about they have less electron on those H on those carbon, or because you somehow adding the magnet on the B0. Yeah.
So if there was no oxygen there, they would both be oxygen.
Yeah, if you don't have oxygen here, if you have simply like replace this one by C3, then this C3 pretty much have the same temperature. And you can see the electronegativity influence sometimes very easy to see. Okay? You compare like this aldehyde with a ketone, right? And let's see the carbon-13 AMR. So the carbon-13 AMR usually design the chemical shape of this carbon here. So this carbon here, this carbon here. Now, if I tell you the result like this, so the aldehyde have a liver-like less chemical shape, which means more shielded than the ketone, which is more de-shielded because you have a liver large number 2 weight. So why the ketone has liver large number compared with this aldehyde? Very good. Yeah. Carbon is more electronegative. You see the only difference between these two molecular structure, here is H, but here is what? C3. So the next spectroscopy is about infrared, the IR. And we will use a lot IR in the lab. IR is based on the chemical bond vibration, okay, like stretching, binding. So those energy is relatively easy to measure. So what we want to learn in this IR is those different region. IR spectroscopy you see in the last example depends on the strength. Usually you will see those signals goes up, maybe more absorption or maybe more like emission. But here you will see this it goes down. But anyhow, you have when you see those kind of signals, that means you have like more absorption. And those we call them wave numbers, but actually they are frequencies. They tell you like one for the wavelength. One for the wavelength obviously is proportional to the frequency. If you want to really calculate the frequency we call that nu. So this is the frequency. That frequency will be c divided by lambda. But here we take away this c, and we just simply take 1 over the lambda. But lambda usually in meter, but here you see in centimeters. So therefore you see those numbers per centimeters, or centimeter maybe 1. So the larger the number, even though this number here, so therefore this number, the 1 over lambda, just tell you the corresponding to your frequency. So the larger the number, that means you have a higher frequency. For us, just to understand, when you have a larger number on this side, which means your vibration is like stronger. Stronger, that means either because you have a stronger bond or you have less mass. So you will see in the hydrogen about 3,000 or something, you will see the bond pretty much OH and HCH, you will have that H. Even though they are single bond, but because you have the small atom H, so the mass is small, even though the bigger bond makes them vibration frequency higher. So then if you don't have H, you have some other atom, carbon atom, oxygen atom, their mass is even more. And so therefore there you can just use their bond strength. When you have a triple bond, and your vibration will be more like stronger, so therefore you have a higher wave number. When you have a double bond, again you are like weaker, and single bond and weaker and so on. So this general patterns.
How much would triple bond be then?
Have a triple bond.
Stronger or weaker?
The triple bond will be stronger. You can see the triple bond here, CC triple bond, CN triple bond. But that means you have the same similar mass. So you compare CC triple bond, you have a higher wave number compared with the CC double bond. But those, even though they are stronger, CC double bond and triple bond is very strong bond, the energy is very strong, but the mass of carbon is not much higher than the mass of H. And you see those basic like physical rules.